Welcome to the lecture series in soft computing in computer science. So this lecture we are going to deal with genetic fuzzy system part 2. So in the previous lecture, so what we have seen is, we have seen how a simple genetic algorithm is used to design a fuzzy classifier model or GA based fuzzy system, right. So why it is simple genetic algorithm? Because here we use the basic fundamental version that uses binary string for representation. So if you could recollect the previous presentation, we have used binary numbers both for membership function as well as for rule set, and we have obtained some classification accuracy around 90 to 95. But there are still some scope are there to improve the accuracy from this point to some other improved point. So we can analyze what is the limitations or what is the challenges or how to improve the algorithmic side, because data side we do not have any other part, because the data is completely free from noise, the data is completely normal data. So we do not want to work with anything on the data. So only thing we need to work on the algorithms. So let us analyze the algorithm, that is simple genetic algorithm. In a simple genetic algorithm, the genetic operation plays a vital role. So here let me take the crossover. So first point, the crossover, what is this responsibility of the crossover? The crossover improves the exploitation of the algorithm. So whenever you want to see a new value and you want to exploit that value, crossover plays the new role. And what is the new? What is the mutation? The mutation will bring a new non-existent value. That means it is good at exploration. So for a search and optimization problem, exploitation as well as exploration are most important. When you find a value, it has to be used, that means it has to be exploited. You do not depend on always only the regular values, you always look for some new values, that is exploration. So when you want to locate the optimal or real optimal solution, and it needs a large number of generation to converge, that is the general genetic algorithm, or what we can say simple genetic algorithm or binary coded genetic algorithm. So what we are going to discuss here is how to improve the genetic algorithm performance, particularly with the help of some advanced and problem specific genetic operators. So these three are the advanced and problem genetic operators that can be used to improve the performance of the algorithm. Gene cross swap operator, gene inverse operator, gene max min operator. Of course, you can find enormous amount of genetic operators in terms of crossover, mutation and selection, both for binary coded version as well as for real coded version. So here in this improved genetic algorithm, we do not work on the representation, right, we work on only on the operation, right. So we have included additional operation in addition to standard crossover, mutation and everything. What are those additional operator? Gene cross swap operator, gene inverse operator, gene max min operator. These three operators are essentially suitable for, see for example, the first operator GCSO, search for alternative alleles, exploiting information even stored in the low fit strings. And what is this GMMO? It tries to identify the binding control, right. What is the performance of searches for the bit structures of improved performance that exploits the new areas of the search spaces. So each and every operator are treated as a somehow advanced version of the operator, and it is more problem specific genetic operators. So if you apply these three operators, definitely it is expected that some good amount of operations can be we got from the algorithm, right. Now coming to the performance of the algorithm. So when we compare the performance of the algorithm, if you see that now the accuracy is 98.98 percentage, 93.26 percentage, 96%. So again the performance is varies from some more improved version. So 147 is the correctly classified data for iris, 166 is for wine and 285, see like this, right. So when you want to analyze the performance of a particular classifier model, you need to check the learning ability as well as the generalization ability. right. So learning ability tries to improve the values, whereas generalization ability try to exploit the values. So these both are very essential, and this plays the most important role for the improved version of the genetic algorithm. Even if it is said that improved version, still lot of scope. See the generalization ability of wine data, here we got only 93.33%. So there are lot of more scope or there. Here 96%. Almost for iris we may treat that it is settled down. Still for iris also, because it is a very simple data and linear in nature, it is very possible for the string iris data to reach 100%, because NN proves, neural network model proves 100% accuracy. So what about the fuzzy logic classifier model? So both are soft computing based approaches. Even that NN performs the 100% accuracy, FLC model why not? So here a question arises, when I should go for NN based approaches, when I go for FLC based approaches. If NN is an approach which will be treated as a block box approach, you will give the data, the data will be processed and the outcome you have been receiving it, but why that outcome has been receiving it, you are not aware of it. But when you take the fuzzy classifier model, because of the requirement of fuzzy conditional statement in the form of if then rules, we may treat that the fuzzy classifier model has some interpretability when compared with the neural network models. But even then accuracy is a major important factor. So with the NN we can achieve 98, 99, even 100% accuracy. The same accuracy should be also got from FLC, but we are get stuck in 98.6 for iris data, 93. So it means that still some scope are there. As I already said, we do not want to work on the data, because data is natural and we do not disturb the data and its schema. What we can do is, again we can think about the algorithm. So this IGA algorithm is the improvement of SGA algorithm in terms of genetic operations, right. So here improvement is made by means of operation, some more and advanced operator has been included and specified. Let me discuss one more algorithm that is based on representation strategy. So this is the optimal MF and rules obtained by the IG algorithm. If you compare this MF as well as the rules with the SG algorithm, you can find a lot of differences and lot of minor adjustment over the values. P1 you can easily verify the P1, P2, P3, P4, P5, P6, you can easily verify these points with that is obtained for a variable with respect to SGA and IGA. There are some minor adjustments are there in order to accommodate the overlapping ratio, as well as in order to accommodate other kind of functions and everything, right. So with this, what we can understand from that is, with the varying kind of problem specific genetic operator, we bring some improvement, but still there are a lot of scopes for improvement. So what is the next algorithm that can be discussed here is a mixed genetic algorithm. What is meant by mixed genetic algorithm? Here in the representation we are using the mixed representation. Say for example, for membership function we are using real numbers, and for rule set we are using binary string. Why? Because there is a well known problem associated with the conventional binary coded GA. The conventional binary code GA has a problem called Hamming clip problem, which cause difficulty in case of holding continuous variables. Suppose if your data, say for example temperature is one variable, the temperature is 70.6, 70.8, 80.1, 80.5, like that. If the temperature is continuous variable, let us take an example. If you want to code, that means if you want to convert the binary value into its equivalent decimal fractional value or continuous value, you may face a problem called conventional Hamming clip problem. But for discrete variables with the total permissible choice, suppose if you have a variable that is a discrete value, so if you want to accommodate all the discrete variable values with the binary representation, then the permissible choice is maybe 2k level. So you may go for more number of representatives, again it is becomes a difficult. So these are the two demerits associated with the binary coded GA when you represent using binary numbers for all the solution variables. So what we can do, we can go for some problem specific representation. Here the membership function always take a value P1, P2, P3, right. So it means that it can be represented using real numbers. Rule set what it will take? It will always take either low or medium high. So it may be represented by using binary string. So with this mixed form of representation, so if you do the simulation or if you do experiment is using this kind of modified version of the algorithm, that is a mixed representation genetic algorithm, the representation looks like this. See, the membership functions are represented as real numbers, right? What about the rules? The rules are again the binary numbers, because it is going to represent the low, medium, high, only these three values. But here this representation is quite different, and it is going to represent the real numbers. That is what essentially needed in order to bring improvements in the approaches. So the genetic operators, maybe we can try with some improvements if you are not convinced with the result obtained. So for binary string, 2-point crossover and gene crossover operator, these are all trial and error based one. This operator we can apply and check the results, or we can remove that operator, we can apply some other operator, we can check the results. Like that you can go with the crossover and mutation for rule set. And for membership function, the crossover is arithmetic crossover, and the mutation is, since we are using it as a real number, right. So this is the genetic operations that we have introduced for this new version of the algorithm, that is mixed genetic algorithm. And if you could see that the convergence characteristics, this is this blue line represents the convergence characteristics of simple genetic algorithm. The green line represents the convergence characteristics of improved version of the genetic algorithm. And if you could see that the convergence is very faster with respect to mixed genetic algorithm. So the problem specific representation also plays a vital role in bringing. See, if you use binary values, there is one more overhead is there, right? Converting the binary values to real numbers and then evaluate the fitness value. So that burden and that overhead is reduced, and it is evidently seen from the convergence graph. So it is converging very quickly. See the curve, if you look at it, it is converging very quickly, and it's attain the saturation level very faster. So from this we came to understand the idea that the simple genetic algorithm can be modified either in terms of representation or in terms of operations. So either way you can do it, or some other strategies are also available. You can look at the literatures where the genetic algorithm can be, that is where the basic genetic algorithm can be modified in order to bring some improvements in the results of your desired problem. So look at it. See, now the SGA has 97, whereas MGA 98.6. See here, we have obtained the 100% accuracy for the generalization abilities. I told you in the previous slide, right? Iris data, it is very easy to obtain 100% because neural network has obtained. So also look at the rules. The rules are very simple, right? With only few variables in the antecedent, we are able to discriminate the class label. Let me come to the wine data classification. See the improvements, 95, here it is 96. So it means that still some scope and possibility is there. You can bring some more algorithms into the mixed genetic algorithm, so that we can bring lot more advancement in that. With respect to see the for the DCB dump data classification, we have obtained 98.98%, and you see the rules is very simple and very easy to code also. So what I am trying to convey to you is, when you apply an algorithm to train a fuzzy classifier model, so you always think about how to improve the performance of the system by improving the operation, representation strategy, and much more things in order to show the improved results. If you could see that there are some problems with RGA. What is RGA? So RGA is real coded GA, real coded GA, right? Because still I said that some scopes are there for improving the results of the classifier model, right. So what are the problems with RGA? Maybe problems of local optima, or sometimes it may consume more time, or another important thing is it has more number of parameters to achieve, and most importantly genetic algorithm didn't have a memory capability, and also it failed to retain the diversity in the population. So when the data set is very dynamic, that means the values are keep changing over the period of time, or if the values are many new unknown values, see the RGA feels very difficult and RGA is very problematic. So what you can go is, you can go with PSO. So because PSO is having the memory capability, with one advantages of PSO, because when PSO is completely real coded, whereas in GA you can go for binary, or you can go for real, or you can go for integer, or you can go for mixed number of representation. Whereas in PSO the basic version comes with real coded. but still the PSO is having some weaknesses. What are the weaknesses? See, it converges rapidly during the initial stages of rest. It means that it is again local optima, and that means very local optima. So because of the premature convergence, premature conversions. And another thing is, when it is solved for very complex data classification, it is always get trapped in the local. See, these are the things that makes the PSO also failing is. Even though PSO is powerful and the genetic algorithm is also treated as a powerful algorithm for doing the optimization, it has its own pros and cons. So what one can do is, we can try with hybrid GA-PSO approach. So we may treat them as intelligent genetic algorithm. Why it is intelligent genetic algorithm? Because a new kind of mutation operation can be introduced that has been inspired from the PSO operation. What are the operations in PSO? Velocity as well as position updating operation. That velocity and position updating operation can be brought and as a mutation operation, and it is can be included into the genetic fuzzy system. So accordingly, the algorithm is called intelligent genetic algorithm. On the other hand, you can say that enhanced particle flow, the basic version of particle flow optimization algorithm, in that you can include genetic operation. You know, the fundamental operation in genetic in particle flow optimization is velocity as well as position updation. In addition to that, you can also include crossover, mutation and everything. And if you observe the performance of your system, this enhanced particle flow optimization is good at accuracy, and this intelligent genetic algorithm is good at interpretability. So what is this intelligent genetic algorithm? So you want to include the memory capability for GA. So the usual procedure of velocity and position updating equation is additionally incorporated into the genetic algorithm. So that is the way in which you can make the genetic algorithm still work more efficient. Why it is treated as intelligent? Because it retains the memory, it retains some sort of memory, right? So based on that, see here, no need for initial weight, old velocity and consistent operator, because it is going to act as a kind of mutation operator, if you could see that equation, because here one factor is there, so that factor is needed, so no role for initial weight, because no needed, right? Because that value is meant for guiding factor in PSO. Here the guiding factor in PSO is just an operation. Already we have an operation, we want to introduce a new operation, that is the PSO based operation, and this PSO based velocity update and operation is treated as a mutation, so this is sufficient. What about enhanced particle swarm optimization? Apart from the velocity and the position updation, this is a general flow of a particle swarm optimization, general flow of a particle swarm optimization, and in that particular problem we are applying the crossover, we are applying the mutation, and then we are doing the G best and P best to find out the new position and velocity. So with the application of these two operators, now we can treat this G as a enhanced PSO. Now we got two algorithms, right? One is IGA, another one is EPSO. EPSO is nothing but enhanced particle swarm optimization, and IGA is see, all these are like a plug and play method. Some operators has been taken, modified according to this algorithm, some representation strategies can be modified according to the data. So everything we can do it on a like a game way method and try to observe the results. At one point of time, a new combination, a new improvements that you brought into the algorithm in terms of enhanced, in terms of improved, or in terms of intelligent will bring the good results to your fuzzy classification system. Let me revisit the fuzzy expert system once again, because here in this aspect we are going to discuss about some more hybrid version, complicated hybrid version. In the previous thing also it is a hybrid, right? Genetic operation is brought into PSO, it is enhanced PSO, and PSO operation is treated into genetic, so we treat it as a hybrid GSO. But still more complexity in terms of representation and other things can be included, and in order to include that, we may treat again that if then rules and membership function. So two algorithms can be introduced here. Here one is GSA, that is genetic swarm algorithm. Another one is ABA, that is AND B algorithm. So all these algorithms are meant for still improving the results. Say for example, when you change the data, maybe these algorithms what we have discussed so far may be good for an iris, wine, DCP dump, or KDD cup, or breast cancer data, or some other data. All these data are something like a benchmark data available in the UCA repository. Suppose if I want to go for some complicated problem application oriented data, let us take an example of a microarray data. That data is the one that is essential for treatment of the cancer, and it is the information about the cancer patients. For such kind of data, maybe these microarray technology based data may also available for diabetes, also available for rheumatoid arthritis. So for such kind of complicated and more large amount of data, this simple combination hybrid GA-PSO in terms of operation alone is not sufficient to address the classification of these complicated highly responsible data. So what we can go for is, we can go for GAC and let us shortly I introduce what is GAC algorithm. See how the GA algorithm starts. It generates the initial population, it evaluates the fitness of the evaluation. If the fitness is converged, you can stop the process and return the best value. In case if not possible, you can apply the genetic operation. Now here the genetic operation is applied by splitting the population into two. For rule set we are using binary string. For membership function you are using the real value. So for membership function you are applying the PSO. In addition to that you are applying the generic crossover operator, and for rule set you are applying the binary string. Since it is binary string you are using the improved. Say this is the IGA, right, and this is the enhanced PSO. So now this IGA plus enhanced PSO is forming a new combination, and this new combination can be called by the genetic. Why? Because the population is split into two. In IGA there is no splitting of population. In EPSO there is no splitting up. The operation is applied on the entire population, but here a small novelty is introduced, that is splitting the population into two, and we are doing the same thing. Again if you could see that here also this floating point works good, but what about this binary string? It may fall into a problem called Hamming clip problem, right. So what the algorithm introduced again in order to improve the performance is AND-B algorithm. So the same procedure and splitting a population. In one side you are using the AND colony optimization, and in the other side you are using the artificial B colony algorithm. So ACO, because the rule set is represented as integer number. So if you look at this algorithm, that is AND-B algorithm, if you see the flow chart, see this is the general statement: generate the population, evaluate the fitness, and if you check whether the idea is converged or not, and accordingly you need to design. If it is with the population, see the population is split. In the previous case IG and EPSO is combined, but here AND colony optimization, because I already told that AND colony optimization is very good at combinatorial optimization. Here it is common. So what is rule set? Rule set is going to do whether it is low or medium or high. At any point of time it will take 1, 2, 3, either one of these number. It is a combination, right. If it is if one variable is low, another variable is medium, another variable is high. Maybe in one variable is low, another variable is also low, and the third variable is high. If one variable is medium, another variable is also medium, and the third variable is high. So it is going to take the combination, right. So we may treat this problem of fine tuning the rule set as a problem of combinatorial optimization, and you can apply AND colony optimization into this algorithm. So this is the process of AND colony optimization. You can revisit our previous lectures where the basic fundamental version of AND colony optimization is discussed. And when you come to this ABC algorithm, you can the basic version is also already discussed, but here the combination of ACO and ABC has been brought in by splitting the population, where the integer number representation you apply ACO, and for floating point representation you apply ABC. On the whole, the algorithm is named as AND-B algorithm. So this is a new algorithm. It also tries to bring some improvements in the approaches. See, this is the rule set for a cancer data, for a NGT, for a diabetes data set generated using microarray technology, and this is the same for same data. So it means that the rules, even though it is good at classification of the data that is taken for consideration, we need to focus on the compactness of the rules. I already told that interpretability is one side, and the other side compactness of the rule set is also plays a vital role. This AB algorithm, this AB algorithm is producing very compact rule set when compared with the CSC approach. Like this, see, on the whole, these kind of approaches are optimization. Whenever you work for optimization, you should always think in a greedy manner, something better than that, something better than that. Is there any possibility to obtain this? Is there any way we can modify the existing one so that we can obtain better than this or not? So like that we can always think about that, since it is an obtain. So with respect to GSA we can have obtained certain things, and with respect to ABA we have still improved a better idea. Now in the fuzzy modeling we have two contradictory objectives. One is interpretability, another one is accuracy. When you focus on linguistic fuzzy modeling, that means you take the interpretability as the main objective. So your focus is on improving the accuracy. When you work on precise fuzzy modeling, so your objective is accuracy and you work on improvement. But these two are contradictory. When you focus on accuracy improvement, you lost interpretability. When you focus on interpretive improvement, you lost accuracy. So there is always a trade-off between. So we tried with a lot of combinations. What are those combinations? We tried with simple GA, we tried with improved GA, we tried with mixed genetic algorithm, and we tried with IGA, we tried with EPSO, we tried with GSA, and we tried with AB. So all these algorithms are, why all these, not only an algorithm but also the problem representation and operations. So based on this problem represent operation, we have varieties of algorithms, SGA and algorithms. So whatever the kind of problem represented I have chosen, different varieties of genetic algorithm. Whatever the kind of operation and the combination of operation, the inclusion of operation or the exclusion of operation from one algorithm, so the operation. So even after doing all these things, we still face this trade-off when we go for different application domains or when we face a different data set, and this is nature and this is very obvious while designing the fuzzy system. So one is linguistic fuzzy modeling, another one is precise modeling, and we need to alleviate and we need to compact this trade-off. So how we can do that? So we can look for some other nature of inspired optimization algorithms. In the literature you can find lot more nature inspired algorithms like fish swarm, artificial immune system, harmony search algorithms, invasive viewed optimization, biography based optimization, artificial bee colony optimization. So like that you can find a lot of nature inspired algorithms where you can try these any one of these algorithms in order to fine tune the results. But what we have done in our research is we have started studying the water. So these kind of pictures, are you familiar, right? You have seen somewhere else, right? Maybe you cannot see this, maybe you are not possible to see this, but this you can see. This is your kitchen sink. This also sometimes you can see in some well or some bore well, right? So what is you observe? You observe some swirl motion, right? You observe some swirl motion. You observe some swirl motion. We observe some swirl motion. So it is understood that water in nature have some swirl motion in it. So the swirl motion of the water is studied and the mathematical model has been understood from the concept of fluid mechanics and from other mechanical aspects that deals with our physical properties of water that dealt with the water movement. So this is the very highly complicated equations, and based on this equation it is very well established by many researchers and many authors, the water movement and the happening of the swirl movement among the water particles. So we studied very strongly this behavior of the water and its associated movement, and what we have do is we came with a new algorithm called water swirl algorithm, and for that water swirl algorithm we have coined a new equation. Say for example, alpha nu is equal to alpha volt, alpha previous positions, and if you look at it, these equations closely resembles the equation of the particle swarm optimization. Say for example, use of reference position performs very well in exploration, and you can avoid the velocity clamping, and if since there is no parameter and it is completely parameter free and different variables have different value, that provides large search space. So all these are very positive points. So here the new innovation is made in terms of operation, that is particularly we have devised a new equation and we call the algorithm as water swirl algorithm. So this algorithm, this single algorithm, now it is going to handle the trade off between accuracy and interpretability. So this is the flow chart. we start the process as usual. Randomly initialize the water particle control parameters, randomly generate position. For each position you do the updation like this, right. So you have to check whether the optimal solution is reached or not, otherwise you have to go for each water particle update the position value, so that the position value will take a swirl motion, and the swirl motion will reach the target of settling down. So this is the idea that we have to understood from the novelty of algorithm that has been derived from the water, that whose behavior of swirl motion in the nature. So using this algorithm we have devised the idea with all the other approaches. So this is the one for obtained for wine data. See, for wine data, see the rules, same thing, obtained by RGA, obtained by PSO, obtained by IGA, obtained by EPSO, obtained by WSA. So for all the cases you can find the idea. So if the color intensity is low and malic acid is medium, then it is fine. If the magnesium is medium and malic acid is medium, then it is fine. See, if you could see that when you want to obtain the optimal rules using various approaches like RGA, PSO, IGA, EPSO and WSA, you can find different formatting of rules, right. So at one point of time it is easier for you to get the rules that is very easy to understood and very easy to follow. And it's the same way you can find the membership function also. So this is the membership function generated using RGA, this is PSO, IGA, EPSO and WS. If you could see that there are some minor adjustment, see how perfect this membership function, that means optimal membership function, this is obtained by WSA. If you could see that there are lot of disturbances, right. See the line here, it is like that, see this like this, see here it is like this, see there are small minor improvements is there over the period of time, over the period of iteration. All these because of effectiveness in terms of representation, effectiveness in terms of operations, effectiveness in terms of combinations, effectiveness in bringing the new novel idea and approaches. So friends, what I am trying to convey to you is a fuzzy system is an interpretable classification system. So in majority of the cases, rather than rely on neural network based classification approaches, you can always rely on using the fuzzy for bringing the interpretability in the classifier model. But bringing the interpretability in the classifier model, you need to devise the rule and membership function from the data. If the data is very simple, it is easier. If the data is increased and the data is very large, if the data contains lot of non-linearities and it has more number of variables and samples, then it is not easier for you to devise the rules and membership function, for which the evolutionary algorithms or nature inference algorithms or the combination of these algorithms with respect to representation and evolution plays a vital role. So whenever you want to design a fuzzy expert system, so you either expect the rules or expect the membership function from an expert, design the fuzzy expert system and execute the system in order to get the results. In case if you do not find any expert over the data, almost all the possibilities are there, then you try to think about the evolutionary algorithms. You may start with genetic algorithm and you can go with any other algorithms up to this point. So with this we come to the end of the session. I hope you are very well understood the idea about how the genetic algorithm as well as other algorithms can be implemented for fuzzy logic. This lecture can be again practically illustrated through MATLAB session. With this I thank you.